This is Lecture 11A. It is a brief introduction to sequences and series. I'm sure you're familiar with the definitions of sequences and series. Usually you start with the idea of a set being a collection of objects, and these objects in a set are called the elements. So for a set, it's just any collection of objects. The objects are called elements. When you move to a sequence, there's several ways to think of sequences. One is to think of them as an ordered set. The elements of the sequence are now called terms instead of elements. So a sequence is a set that has an order to it. Another way to think of a sequence is a function whose domain is the natural numbers, perhaps including 0 depending on how you count. That's another way to think of a sequence, and that's actually much more convenient. When we think of sequences that way, let me get the pen here. Then the notation of the sequence is like this. If you have a function, of course, uses function notation, f of x, right? And then x are the elements of the domain. For function notation, for a sequence, if you're thinking of it in terms of a function, then the elements, you're just given a value a, and then the subscript notation n. I don't know why this is going sideways. Let me erase this and try it again. Pen. So here's a function. That's better. So the function, this is the name of it, of course, and then here is the independent variable. The x are all the x's in the domain of f. When you think of a sequence as a function, then instead of writing f of x and saying that x is some element of the natural numbers, instead you use the subscript notation. So a is the value, and then you put the n down here. So you could in fact write this as f of n, where n is a natural number, and here is your subscript notation. We're so used to writing that subscript you don't think of what it is, but really it denotes the domain of the sequence. If you think of the sequence as a function with a domain that is the natural numbers. So if you were to draw the sequence, 1, 2, 3, then you would just put dots. Right, here's our sequence. So this is, if this is 1, 2, 3, then this of course is A1, and this is A2. In function notation, you would say f of 1 and f of 2. This is a handy way to think of it, because when we're looking at convergence, sometimes we compare the sequence to a function of real numbers that has the same value on the natural numbers that the sequence does. In other words, we just draw a line through these numbers and we look at the sequence, the function that would go through these values. You know, it helps if it has some kind of name, and then you can watch its convergence. So let's move on to a series. A series is the sum of the terms of the sequence. And now we're going to get into an idea of what the sum is. If the series is finite, then you have, of course, you can add the terms up. It will always converge. The series could be infinite if there's an infinite number of terms in the sequence. We also look at something called the partial sums, which is just say the first 10 or the first 20, the first 3,000 elements of the sequence summed up, and that would be the partial sum of the series. On the previous slide, I mentioned finite and infinite series and a finite and infinite sequence. This size of the sequence or the series is extremely important. If the sequence or the series, if they are finite, then you can use the usual rules of arithmetic apply. It doesn't matter how many numbers there are, as long as there's a finite number, then you can use the typical rules of arithmetic. When they are infinite, when you're dealing with an infinite sequence or an infinite series, you cannot assume that the rules of arithmetic as you understand them will still apply. For example, you can't just add them up. How can you add an infinite number of terms? Also, if you think of addition, remember addition is commutative. You can add things in any order. If you have an infinite series, you cannot add the terms in a different order and get the same result because it's an infinite series. So when they're infinite, you cannot assume that the usual rules of arithmetic apply. In fact, this is the basis of these paradoxes. People will put forth a paradox, and usually it's because you take well-known rules in one area, try to apply them to another area in which the rules don't hold. That gives you your paradox. So here, what we're going to do, instead of trying to look into all the paradoxes and resolve them, we're going to find new ways of finding the answers, of finding the sums, looking at the convergence of these infinite sequences and series. In other words, we're going to develop methods for finding answers when ordinary arithmetic fails. Now I want to mention a big notation confusion. As you know, good notation just totally simplifies a problem. Good notation in math is like a good sketch in engineering or physics. So this proper notation is, when you have the notation right, a lot of times the solution just falls out. If you've got bad notation, you just simply struggle. So let's look a little bit at the notation here. So we're going to take a sequence here. Where's my pen? Okay. Here's a sequence, and again, of course, we're using A, and then the subscript n refers to the nth element of this particular sequence, right? So let's say that the sequence is n minus 1 over n factorial. In other words, we have a definition for the sequence in terms of the counter, and that's fine. Now when we go to the series, for the infinite series, we will sum from n equal 1 to infinity. Again, little n equals 1 to infinity will be our counter, using little n as our counter, and then we just put the definition of the sequence afterwards. We're summing it up, right? That looks pretty fine. Now what if we want a partial sum? Or no, let's look at a finite series first. So if we have a finite series, then there aren't an infinite number of terms. Instead, there's only so many, and we typically denote that so many by capital N. This is a lot like the meshing in numerical integration. We tagged lowercase n and uppercase n together. And here we're taking lowercase n and uppercase n together. Uppercase n is the maximum number, and lowercase n is the counter. So we see here, here's our counter, right, progressing from 1 to n, because that's the maximum number that you have. Now let's look at partial sums. A partial sum is, again for my pen, partial sum is a sum from n equal 1 to a finite number in an infinite series. In other words, I'm going to sum over the first 300 or the first 3 million. Right? Now, at this point, you'll notice in the textbook and other places, the notation suddenly changes, and this nice situation that we set up here gets changed. And I want to point that out because that's the source of confusion. Now, when we do the partial sums, we tag the partial sum, we call S as the partial sum, and we tag it by n. And we let n, in this case, be the number of terms we're summing over. So if we have S10, means we're summing over the first 10 terms. All right, now we've let n, in this sense, become the maximum number of terms we're summing over, right? So really, we should call this capital N, but we don't. Instead, it is called lowercase n. So what was the counter up here now becomes the maximum down here when you're talking about partial sums. Okay, so what do you use for counter? You use a different variable j, or I. So now you have I equals 1 to lowercase n of I minus 1 over I factorial. These are dummy variables. It doesn't matter. You can change them around. Actually, don't like this notation. You can tell that probably. I don't like this notation. I prefer to tag all my variables the same unless there's some really good reason for doing it. And the only real good reason for doing this is tradition. Okay, and usually tradition is good. But in this case, well, that's how it is. Okay, so I'm going to go over this again so you can see it. Typically, we use n as a counter. So each term of the sequence we denote with a lowercase n being denoting the nth term of the sequence. When we create the series, we continue using lowercase n as the counter. So that will denote the nth term. So here, right here, is the addition of the nth term to this infinite series. And then the counter now goes from 1 to infinity if it's an infinite series. If it is a finite series, it goes from lowercase n to 1 to big N. All right, and n being the total number of the terms in this finite series. We need to look at partial sums. To do a partial sum, then we sort of abuse this notation. Now we denote S as the partial sum, and the subscript lowercase n refers to the maximum number of terms that we're summing over for our partial sum. Okay, so what was a counter? We now have advanced up, given it a promotion, so to speak, to being a maximum number, the final number that we're going to sum over. Now we need a new counter, and for that we'll use I or J. Now this is the last definition we'll go over in this lecture, and that is convergence. So we're looking here at highlighter. Okay. We're going to apply two terms here, convergence and divergence, to the sequences and the series. This, of course, applies to infinite series and infinite sequence. Right. If this sequence or series converges to, in the limit, approaches a finite number, that means not plus or minus infinity, then the sequence or series is said to converge. It diverges if that doesn't happen, and it can diverge in three ways. First, it can diverge because there's random behavior to it. It just doesn't settle down. Or because it has a very orderly pattern of oscillations. For example, it could be plus 1, minus 1, plus 1, minus 1, plus 1, minus 1. It doesn't approach a number. It's just always oscillating. That's another reason. If this sounds like limits, that's exactly right. And then the third way it can diverge is if it goes off to infinity. So to examine this kind of behavior for the sequences and series, we can use the limits and the limit laws. They will apply to sequences and series. Use the squeeze theorem, sometimes L'Hopital's rule, and then there's a couple new theorems and techniques. And we'll use those to determine convergence and divergence of the series or the sequence.